Hi, Yanine, and welcome to today's lesson on a dynamic equilibrium. So hopefully today, by the end of the lesson, you should be able to understand how a reversible reaction can be at an equilibrium point in a closed system. So, as you can see, there's a nice little diagram on the right, or comic strip, which talks about dynamic equilibrium. You're going to understand what is happening in that hopefully by the end of the lesson as well. But to start with, I want you to try and answer for me these 5 starter questions. So write down the answers for these 5 starter questions. 1, what is formed in a neutralization reaction? 2, what is used to test for pH? 3, what types of reaction are involved in a reversible reaction? 4, what is the symbol for a reversible reaction? And 5, draw a profile diagram of an endothermic reaction and explain the change. So pause the video now, please, and have a go at answering those questions. So hopefully you've answered those questions. We'll go through the answers and correct your answers and write down anything you didn't get. So what is formed in a neutralization reaction? It is a salt. What is used to test for pH? It is a universal indicator. What types of reaction is involved in a reversible reaction? It's a decomposition reaction, and the symbol for a reversible reaction is the arrows there. And then lastly, the profile diagrams or energy profile diagrams of endothermic and exothermic reactions are there. So get those down if you didn't get them correct. So the first thing we need to understand with our learning objective was what a closed system is. Okay, so you might not have come across what a closed system is. So I've got the 3 types of systems that can possibly exist, and I'm showing them using water in a jar, okay, in a bottle. So the first one is an open system. So like my cup of tea, for example, or water in a glass bottle. So an open system can exchange mass and energy, usually in the form of heat with its surroundings. So basically, if I put hot water in there, you'd lose some water vapor out the top, and then you'd also lose heat out the sides of the bottle, okay? So you can lose mass out the top, and then you can also lose heat out from the walls, okay? Or vice versa, you could get heat in if it's a really cold bottle. So that's an open system. The next system we have is a closed system. So in a closed system, you also put a stopper at the top of my bottle here. So in a closed system, it allows the transfer of energy, so in this case heat, but not mass. So even though my water inside can heat up or cool down, even if it heats up, it can't get anywhere, okay? It can't escape. Therefore, there's no change in mass. So that is my closed system, which is what we're going to be talking about today. So the closed system can transfer energy, but no mass can escape or come in, okay? So it's just energy. And then the last one you need to know, although this isn't being used today, is an isolated system. So isolated systems, think about it like a thermos, okay? So nice trusty thermos where you put your tea in when you go for a long walk on a cold day, okay? It doesn't allow the transfer of either mass or energy. So no heat can get in or out, and no mass can get in or out in an isolated system. But the one we're interested in today is the closed system. So only energy in or out, no matter in or out. So reversible reactions and a dynamic equilibrium. So at dynamic equilibrium, the rate of the forward reaction equals the rate of the reversible reaction. So as the forward and reverse reactions are continuously taking place, a state of dynamic equilibrium has been reached. So think about it like this. So our reaction where we have A plus B, and then, so A plus B is the reactants up here, and then C plus D is the products down here from last lesson. So as we start to start the chemical reaction, we start making some products, C plus D, okay? But then because they're a reversible reaction, what actually happens is some of that product goes back into being reactant again. And so even though we think that we're only moving in one direction, and we're making C plus D, you're actually making A plus B again, or the products again. So your products are making the reactants in this one, and then your reactants are making the products on this one, until you reach a point called an equilibrium point. So the equilibrium point, what happens here is that the reaction basically reaches a point where you're not making any more reactant or any more product. The reaction is still occurring at this point. So it's really important to note that the reaction is still occurring at an equilibrium point. The difference is that the products and the reactants are making each other at the same speed. That means that there's no more product being created and no more reactant being created. So say we start off with 100 particles of reactant and no particles of product. Our equilibrium point, we might reach 50 particles of product and 50 particles of reactant. And so if we make 1 particle of a product, we then make 1 particle of reactant. So they're making each other at the same speed. So it's just like running up an escalator that's going in the opposite speed. If you run up to the middle of the escalator and then just move at the same speed that the escalator is going down at, you don't go anywhere. You still have to move in order to stay in that same place, but then in retrospect to the ground, or if that was a staircase, you're not actually going anywhere. So even though you're still trying to go up and the escalator is still trying to go downwards, you're not actually moving anywhere. So that's what a dynamic equilibrium is, okay? You're not making any more product or any more reactant, even though technically they're still making each other. So what I want you to do now actually is to pause this. Hopefully you've downloaded this PowerPoint from Edulink. If not, you need to jump on Edulink and download this PowerPoint. And then you need to open the YouTube video at the bottom of this, okay? As you can see down here, there is a YouTube link. You need to open this YouTube link and watch the video here. It's a really good video, which again explains your reversible reactions. So write down your definition, and then open this YouTube link and watch what dynamic equilibrium is. Okay, so hopefully you watched that video. If not, you need to jump back to the previous slide and watch that video. I'm going to give you a chance now to pause and read the information on this slide. Okay, it's a chance for you to just read the information on this slide. It's about something called the Chateliers Principle. Okay, we're going to learn about the Chateliers Principle, and basically it means that if you change the conditions, you change like the pressure or the concentration, for example, you will change where that equilibrium position exists. So instead of 50-50, so 50 product, 50 reactants, you might go down to 60 product and 40 reactant particles. So you're changing that position either up or down on the graph previously. But pause the video and read this for me. Okay, so hopefully you've read that slide for me there. So the effect affecting the composition of an equilibrium mixture. So he was a very, very smart man, the Chatelier. So again, pause the video please and watch this link for me. It's a really good explanation of Le Chatelier's principle again, and it's just another way in which you can kind of understand what's going on there in a little bit more detail. And again, also you can turn to Caboodle or look for other YouTube videos if you're still not understanding the principle. So pause the video and watch this other video. Okay, so hopefully you've watched that video of the Chateliers Principle and you've read the whole mass of text about the principle as well. So if we look at the diagram here on the right, okay, this chemical reaction. So it's iodine monochloride and chlorine reacting to become iodine trichloride. So this reacting mixture can be changed by adding or removing chlorine from the mixture. So if you've got lots of chlorine gas, it forms iodine trichloride, and then the problem is you then can remove that chlorine gas and it'll go back to being iodine monochloride. So depending which way you want to go, you can either form iodine trichloride by adding lots more chlorine, or you can start removing the chlorine to get iodine monochloride, depending on what you actually want. Do you want iodine monochloride or iodine trichloride? You have a choice, which is the good thing with Le Chateliers Principle. So why is it important in business? And are there any negatives to consider when manipulating reversible reactions? So have a think. You should have hopefully watched some videos, and then I want you to write down your answers, please. So have a think, write down your answers, and then pause this video because then we will talk about the answers. So it's important in business because some businesses, if this business wants iodine monochloride, for example, because that's what they want to create, and they've got iodine trichloride, then it's important that they can make more iodine monochloride than iodine trichloride. And so it becomes financially viable for them to do the chemical reaction if they can remove the chlorine. They get more product than what they would have originally. So in businesses, it's really important that they maximize the amount of product they get, because it's the product that is usually what they want in order to make a profit. And so if they can maximize the profit by shifting the dynamic equilibrium towards the product, so it makes more product than reactants, then that's really important for the business in gaining money. So that's why Le Chateliers Principle is really important for businesses. It means they can get more of the product they want, which means they can increase their profits. Okay, and then any negatives to consider when manipulating reversible reactions? Yeah, it takes energy a lot of the time. Okay, it takes money and energy in order to shift the equilibrium. And so sometimes it's not financially viable to shift the dynamic equilibrium, in which case that they won't do that. They'll just create the products and take what they can. So not all chemical reactions is it financially viable to shift the dynamic equilibrium. There you go. And there are your exact answers if you want. So copy down the answers if you didn't get them or if you got them wrong. So what I want you to do is, again, watching another YouTube video, but before you watch this YouTube video, can you write down the table at the bottom here? So addition of water, addition of hydrochloric acid, and addition of water again, and then observations of color on the bottom. So write down this table of results, please. Write down the chemical formula, which is at the top here, and then you're going to watch this video link that's at the top. And this video link will show you what happens when cobalt chloride is dissolved in water. Okay, and so you're going to be watching the video, and then when you watch the video, you can fill in the table at the bottom. So you can fill in this observation of color down here. Okay, so copy down the table, watch the video, fill in the observations of color, please. Okay, so the two different cobalt ions, so this one here and this one here, so this is a 2+ cobalt ion, this is a 2- cobalt ion. They've got different colors, so you can see which one it is depending on the color. So what happens when they add water? What happens when they add hydrochloric acid? Don't need to fill in the Y yet. We'll get to that. So pause this video and go watch the experiment. So those are just the steps that they followed for the experiment. So if you like experiments, you can copy down these steps. However, it's pretty self-explanatory. You've seen it in the reversible reactions pretty much anyway. And so the dynamic equilibrium experiment, it's not that important that you know this method. It's just in there if you're interested in reading it. So questions though for this: why did the solution stay a red color to begin with? Why did the solution eventually turn blue? Why, with the addition of water, did the solution then turn back to red? So it was red, and then we added water, and it went blue, and then it turned back to red. Okay, so what is going on there? So why is it that color? So why is it that one, and then why is it that one? So it's turning those colors depending on the position of the equilibrium point. So the water is bringing it back towards neutral, and then the hydrochloric acid is taking it down towards acidic. And so it's moving that equilibrium backwards and forwards depending on the concentration of the ions inside it. So depending on the amount of water, it depends on whether it's a positive or a negative ion, which is then changing the color there. So we're shifting that dynamic equilibrium backwards and forwards, or up and down. There you go. So when a reactant, which is the chlorine ions, is added, the equilibrium moves to the right, so more product is formed. So it's blue when there's more product, and then water is added, equilibrium moves to the left, so there's more reactant, and so the solution goes pink. So that's what's happening. It's that dynamic equilibrium shifting backwards and forwards. So hopefully that's enough time for you to get your answers down. If not, obviously you can just pause the video and get them. So, chemical hand warmers. Now, here's your challenge question for me. How do chemical hand warmers work? Rechargeable chemical hand warmers. So, watch the video on rechargeable hand warmers. Basically what happens is you click a little button and they release heat, and then they'll stay hot for a while, and then you need to put them in a bucket of boiling water or pan of boiling water, and then they will then go clear again, and then you can click it again, and then they'll release heat again. So they're reversible chemical reaction is the only kind of hint I'm going to give you there. So you need to try and, in your answer, hopefully achieve some of these high steps, okay? If you're on the H band, you should be trying to get us up to step 6. If you're on the gamma band, you should be trying to get towards a step 8. So we explain the energy transfers in a chemical hand warmer, so exo or endothermic. Explain how the energy transfers in chemical hand warmers are reversible reactions. Step 6, link the reversible reaction of chemical hand warmers to dynamic equilibrium. Step 7, justify why chemical hand warmers reach an equilibrium and when they will reach it. And then step 8, a chemical hand warmer does not reset if put in a pot of boiled water. It turns clear, but then turns back to the hardened cold chemical once removed. Why does it have to be put in a boiling pan for 5 minutes to turn it clear and stay clear? Okay, so have a think about why it needs to stay hot for a really long time. That's not an easy question to answer, but have a think about that. So if you just put it in and then it goes clear and then take it out, it will then go back to cloudy again and will release a little bit of heat. But if you keep it in there for 5 minutes and then remove it, it then won't go cloudy again. So have a go at answering those questions. Pause the video now and answer those questions, and use this slide to guide you. Okay, hopefully you've answered those questions. We're going to go on and mark those questions now. So you need to mark your own. So 1, the reaction does not start until it receives activation energy from the silver disk. So when you click a hand warmer, that silver disk gives it the activation energy. The activation energy starts the reaction when the particles then collide with enough energy to have the effective collisions. The reaction is an exothermic reaction from A to B to C plus D. The reaction releases energy into the surroundings, so exothermic. To recharge the hand warmer, it is an endothermic reaction where it absorbs the energy from the surroundings. The endothermic reaction therefore needs to be heated for an extended period of time to absorb the energy. The energy absorbed in the reverse reaction is equal to the energy released in the forward reaction. And then extension, the reaction is not recharged in the reverse direction by boiling water as it absorbs the energy. However, it's not enough to shift the equilibrium from C to D to A plus B, resulting in the reaction occurring again and not remaining as A plus B. You basically need to shift the reaction completely to the side of A plus B, so there's no reactant left, there's no product left, otherwise it will move back to dynamic equilibrium. Okay, so you need to shift it the whole way to just reactants by recharging it a really long time, otherwise it will move back to dynamic equilibrium in the center. Okay, hope you've enjoyed that lesson. There's some extension questions here, so if you've still got some time, have a go in this lesson. Have a go at these extension questions. If you don't have time, don't worry about these extension questions. But if you've got plenty of time, have a go at these extension questions, and we will mark them on Friday's lesson.